somebody posted something in the chat. Could you run through the main ideas from 1B on 6B? Absolutely, I can do that. So before I do that, let's talk a little bit about something to do with the final that came up in this conversation that I'm having with Chatterjee, which is some of the questions that you guys get asked about working with an orthonormal basis, working with the Gram-Schmidt process, is to actually produce a concrete orthogonalization of a vector space. And while I think it's important to do that once or twice in your life, I find that to be a really tedious question to ask somebody to do on a test, to take a set of vectors and orthogonalize them. So I'm not going to ask you to orthogonalize a set of vectors on an exam. I want you to know you can orthogonalize a set of vectors, but I don't actually need you to do it. You know, you need to know something about the fact that these orthogonal, you know, how an orthogonal decomposition works, the relationship of the vectors to each other. I might ask you a question where you start with an orthogonal basis and you've got to do something with it. But I don't know. Actually, running the Gram-Schmidt process is really irritating. So I don't want to grade. I don't want to grade it. I don't want you to do it. I'm going to put my focus on more abstract questions. All right, so Brandon, you asked about 6B, so 6.1, 1B. Wait, sorry, maybe I missed what is the specific question here? Oh, 1B on 6B. I'm an idiot. Okay. All right. If you guys are, whoever it is that's not muted right now, if you're having a conversation, would you mind muting yourself? Do I have to do it? Whose mic is on? All right. Okay. Show that each orthonormal basis R2 is of the form given by one of the two possibilities in part A. Okay. Well, this boils down to showing that there's only two possible orientations of vectors, really. And so the idea here is that you have to ask sort of, I mean, essentially what you're doing here is you're saying what order the vectors come in, right? So if you have something like V1 and V2, so this is 6B, 1B. One of the arguments you can make here is that, so what you're trying to do is you're trying to show, okay, so certainly it's the case that cosine of theta, sine theta, comma, cosine of theta minus the sine theta, that those vectors are orthogonal, orthonormal. Yeah, did I have this in the wrong order, don't I? I made unit vectors, but not orthogonal vectors. Minus sine theta, cosine theta. And on the other hand, I could have cosine theta, sine theta, comma, sine theta, minus the cosine of theta. And so what this represents is two different orientations of an orthonormal basis. So the question says, prove that every orthonormal basis in R2 falls into one of these categories. And so one way of doing that is to say, if you have a V1 and a V2, and they're orthonormal to each other in R2, what is the angle between the vectors? That's the first thing to start with. What must the angle between these vectors be? No. 0. If there's 0, that means they point in the same direction. 90. There we go. That's better. Yeah. So so the idea here is that in R2 specifically, orthogonality corresponds to a right angle in the way you think about it. So there's only two ways to make a vector that is right angle to V1, and one of them is that you rotate this way by theta degrees to get V2. So that's one orientation of the vectors, is that the first vector and the second vector have the relationship where the second vector sort of rotates clockwise to V2. And the other way that you can get a vector that it's a right angle is you can rotate to 90 degrees in the counterclockwise direction. And so then the picture that you need to draw here is how you, I mean, this is basically the core of what this argument is. This is the only way that you can construct. So the first piece of the argument, or one way to do this, is to say, these are the only two orientations of perpendicular vectors in R2. You start with V1 and either you rotate clockwise to get V2 or you rotate counterclockwise to get V2. And then all you need to show is that, like, if you started with the vector cosine theta, sine theta, and you rotated theta degrees counterclockwise, you get one of those other two vectors. And if you rotate clockwise, you get the other one. Does that make sense? Cool. All right, any other questions like that I can answer?
I have a question. Sorry,
you can go. So I was just going to say, could you go over 5C number 10?
5C number 10. Okay. So 5C number 10. Okay, so suppose V is finite dimensional and T is LV, lambda 1 through lambda V distinct non-zero eigenvalues of T. Prove the dimensions of the eigenspaces add up to less than or equal to the dimension of the range of T. So the idea here is that, like, the set sum of the first observation, if you're going to do this, is you already know that for any lambda I that is distinct from lambda J, you guys learn that these that vector spaces don't intersect each other, right? Eigenvectors associated with different eigenvectors are linearly independent. And what that means is that if you look at the set sum of lambda I T and lambda J T, and if lambda I are not equal to lambda J, but this is actually a direct sum plus the lambda J T. Okay, so that their eigenspaces are subspaces. They're a direct sum, right? So they're subspaces that are linearly independent. They live inside, they intersect only at the zero vector, and they live inside of V. And so the idea is, if you know that the eigenspace, if this is true, this is the same thing as saying that each one of these things has the property that it intersects only at the zero vector, and they're subspaces. And so this thing, you took them all and you add them up, this is a set of mutually linearly independent. This is a subspace because it's a direct sum of subspaces. And there's no intersection at all between these subspaces. And one of the things that you guys learned, so whatever this is, whatever this space is, it's a subspace of V. It might be equal to all of V, but it doesn't have to be equal to all of V. So this is equal to subspace W, which is contained inside of V. And then you can use the theorem about the way that the dimension theorem on subspaces. These don't intersect with each other. So the dimension of the direct sum is just equal to the sum of the dimensions of the direct sum pieces. So the dimension of, say, the direct sum of the E lambda ITs is equal to the sum of the dimensions of the E lambda ITs. That's the way it works when we're working with direct sums. And then that must also be equal to the dimension of W, but since W is contained in V and not necessarily equal to V, the dimension of a subspace is always less than or equal to the dimension of its containing space. So that must be less than or equal to the dimension of W. So the core observation here is that this is a direct sum setup, which means you can just take the dimension and break it up across the pieces. Does that make sense?
Yeah, thank you.
Cool. All right, Tu, did you have a question?
Yes. I have a question, but can I ask you about this problem real quick?
Sure.
I did this problem, but I used the theorem where dimensions of these eigenspaces is less than or equals to the dimensions of the space V. And then I used the the theorem where dimension of B equals the rank nullity theorem.
Oh, sorry. Yeah, sorry. There's another piece missing here. I didn't see that this was less than or equal to the range of T is involved in this as well, right?
Yeah,
So yeah, the part that you're doing here, sorry, I completely missed the fact that this was a range of T argument. That's completely on me. I'm sorry, Lindsay. Right. So the idea is that all of the eigenvectors are, the eigenvectors themselves, or linear multiples of the eigenvectors, live in the range of T, right? So the range of T is in the span of these eigenspaces. That's the idea of that, right? So that's what I think that too. That's what you're suggesting here, is that like you're trying to get the range of T into the picture, right?
yeah. So like to show that, but by using the rank nullity theorem, essentially I need to show that the dimensions of null T is only 0, right?
Well, it's possible for, I mean, the null space of an operator. So this is okay. This question is more complicated than I made it. So I'll have to sort of think about it for a second. The null space of an operator as actually corresponds to the eigenspace associated with 0, right? In fact, we showed that on the last exam, I believe, right? Was that on the last exam, I think I gave you guys a question that said to prove that like the null space of we've had this question about invertibility and 0 being an eigenvector. So the idea is that like the null space of an operator is equal to the eigenspace associated with 0 of the operator, right? That those are the same space.
Yes.
Okay. And yeah, so what I'm sorry, I missed what your point was in that question. I
Oh, yeah,
apologize.
no worries. So like your equations, right? Is less than or equals to dimensions of B.
Yeah.
And then I replace dimension of B with dimensions of null T plus dimension of range T, because I want to get dimension of range T into the picture.
Yeah.
So I want to show that dimension of null T equals to 0.
Well, the thing is, you don't know that, right?
So like, is
If
there,
the dimension of the null space of T is equal to 0, then that actually means that I mean, that can happen. If the operator is invertible, that's certainly possible. But I don't think we have necessarily an invertible operator here, right?
okay, so how can
question-
you argue that then?
Go ahead. Sorry, somebody.
On the question, it says that the eigenvalues are distinct and non-zero though, so
Oh,
couldn't
it
you
does say
say
that.
that T is
Okay, now
invertible?
I'm a total idiot. So yeah, so this is the problem with like yeah. So okay, so we know that the null space of T is equal to the eigenvalue of 0. We know that the lambda I, so 2, you're totally correct, right? Because lambda 1 through lambda n are eigenvalues, but they're non-zero eigenvalues. So we have an operator that has distinct non-zero eigenvalues. Well, if it has distinct non-zero eigenvalues, then that means that the eigenspace associated with 0 is just the 0 vector. Which is, I mean, that's it. There's nothing in it. And that means that the null space of T is equal to just the 0 vector because these spaces are the same. And that means the dimension of V is equal to the dimension of the range of T plus the dimension of the null space of T. That this is equal to 0. So these things are the same. So you can use the same argument that I did, but now the V here is actually equal to the dimension of the range of T.
Okay.
Dr. Talida, the question doesn't say that.
Am I on the
0 is
wrong
not
question?
eigenvalue. It doesn't say that 0 is not an eigenvalue.
Oh. Okay. Okay. Let's just erase all of this and let's be careful with the way we're doing this. So all 3 of you are correct at the same time. And I am doing a terrible job of reading this question. So let's actually say what this question actually says. And let's stop noodling around here. Okay. Which is totally on me. You guys are asking great questions. Thank you for pointing out. What does we actually have in the question? We have 0 is possibly an eigenvalue. 0 is possibly an eigenvalue. And lambda 1 through lambda n is equal to all of the non-zero eigenvalues. So we haven't excluded the case that 0 might possibly be an eigenvalue, because what it says is let lambda 1 through lambda n M designate or the distinct non-zero eigenvalues. So everything that's non-zero, we're going to label with lambda1 to lambda n. Okay, so it's possible that 0 could be an eigenvalue. Now, one thing we do know is that, so we know that the dimension of V is equal to the dimension of the range T plus the dimension of the null space of T. And secretly, I also know that this is equal to the eigenspace of 0, which may exist. Okay. Okay. On the other hand, we know that all of the eigenspaces of the direct sum of all of the eigenspaces of the operator live inside of V. So we're going to say the eigenspace associated with 0 of T plus the eigenspace associated with 1 of T, direct sum, up to the direct sum of the eigenspace of lambda m with T. That direct sum, now including the possibility that 0 is an eigenspace, that is definitely a subspace. That's equal to a subspace W, which sits inside of V. Are we okay up to here? So I think this is actually what you were trying to do. I'm just going to add the step, the eigenspace of 0 here. This step basically says you take all the eigenspaces, the direct sum, so they're a subspace. They sit as a subspace inside of V. So now what do we do? Well, if we apply the dimension theorem, we get that the dimension of all of this crap, 0t up to e lambda mt, is equal to the dimension of W, which is less than or equal to the dimension of V. On the one hand, we get now the dimension of the eigenspace associated with 0 plus the dimension of the eigenspace associated with lambda 1 up to the dimension of the eigenspace associated with lambda m. Notice that the dimension of the eigenspace of 0 is still over here. By the argument that that 2 made, this is less than or equal to the dimension of V, but the dimension of V by the the fundamental theorem of linear maps, this is equal to the dimension of the range of T plus the dimension of the null space of T. But the dimension of the null space of T is the same as the eigenspace of 0. So what do we get in the end? We're going to get this inequality that looks like this. Well, notice I have a dimension of the eigenspace of 0 on one side of this inequality and a dimension of the eigenspace of 0 on the other side of the inequality as well. Since it's on both sides of the inequality, I can subtract, and what you end up with is the dimension of e lambda 1t up to the dimension of e lambda mt is less than or equal to the dimension of the range of T. And that's sort of the top to bottom of this argument. So all three of you guys contributed pieces to this, and thank you, Chandradeep, for pointing out that the logic did not exclude 0 as an eigenvalue. Does that make sense?
I have a
Like,
question.
did you follow what I did there too?
I have a question. I did not do it this way. I was just trying to show that T of V goes to 0 when V goes to 0. I mean, like,
So
that
you,
can be
but that, so by doing that, you're making the assumption that T is an invertible operator. And so
okay.
that you can't do that. The fact that the eigenvalue associated with 0 occurs on both sides of the equation is really important, because even if it's there, it's on both sides, and so it cancels out. The T here is not an invertible operator.
So why, can I ask you why you introduce E of 0 T here? Like, because it said lambda 1 to lambda m's are all the eigenvalues that you have. Then
They're
why-
all, no, it doesn't say that's all the eigenvalues that you have. It says everything that's not 0 is in that list, but it's still possible that 0 could be an eigenvalue as well. That's not excluded by the logic of the statement. You're getting confused in the same way that I did. Just because we say that so it's possible that 0 could be an eigenvalue, it's just not part of that list that goes from lambda 1 to lambda m. So if I have an operator that has eigenvalues 0, 1, and 2, lambda 1 would be 1 and lambda 2 would be 2. And then 0 would also be an eigenvalue, but we're kind of leaving it off to the side.
Oh, okay. Okay. Thank you.
Kennedy?
So as far as we're assuming that the dimension of E0T is 0, right?
We are not assuming, we're not assuming that the dimension of E0T is 0. The point is, it doesn't matter. If it was equal to 0, the operator would be invertible. The
Okay.
fact is, it doesn't actually matter if it's equal to 0 or not, because it's on both sides of the inequality. So yeah, if that's not 0, if the dimension of E of 0T is not 0, it's okay because it's also on this side of the inequality. So it will subtract away.
So it'll cancel it out.
It
either way.
cancels, yeah. So the central idea here, the most important idea in this proof is the fact that the dimension of the null space is the same as the dimension of the eigenspace associated with 0.
Okay, thank you.
And then Morgan, was that you that said something? Somebody said something else that I didn't catch. Lily, yeah, it doesn't matter if null space is, exactly. It doesn't matter if null space is equal to 0, since regardless of what happens, it just cancels or it doesn't cancel. I mean, it'll cancel in every case, whether or not it's equal to 0 or not. Yeah, so actually a good lesson to take away from this particular exercise is the mistake I just made, which is don't read hypotheses into a theorem that aren't there. And if you happen to, I'll try to be unambiguous about this, like on the final. If you do happen to get into a question in the final, it's not clear the hypotheses that I want you guys to assume, make sure you ask if you're allowed to assume something or not. All right, so I am going to, I can take one more question if people have one, if it's a quick one, and then we'll move on. Is there any last question that I can answer, like a quick question? That was intended to be a quick question, but I noticed that one I don't think has a widely distributed answer on the internet. So I think maybe it was hard to look up to see what the key idea there was.
Do you have office hours tomorrow?
I am not going to be back until right before class. If I manage to get in before 2, I will post and I'll be in my office. I'm just going to go directly to school. So driving back from LA, as soon as I'm in, I will go straight to school. And if I'm in my office, I'll announce it. You guys are welcome to come by. So I think I'm gonna leave at 8. And it should be enough time to get there by 2, but like that traffic through Santa Barbara is pretty gnarly. So I'll do my best. I'll definitely be there by 3. But I'll make up for that because I'm gonna have office hours on Friday that I'm gonna announce. So I'll have office hours on Friday, and I'm gonna hold office hours at least a couple of times during next week. And this assignment that you guys are working on right now, you don't actually have to turn in until next week.
Oh, so this isn't due Friday then?
I mean, originally I was going to make it through Friday, but this is the one that covers 5C and all the 6 stuff, right? So
Right.
Yeah, just it's important that you work through the questions more than, I mean, you're not going to get it graded with feedback fast enough for it to be useful. So why,
All right, thank you.
you should just get your feedback directly from me. All right, so if we're done with that for now, I would like you guys to, let's turn the page and let's talk about exactly what I want you to know about the Gram-Schmidt process, right? So the last time we talked about what the core idea of the Gram-Schmidt process was. So we're back in 6B. And the core idea of the Gram-Schmidt process was it gave us a way of taking a basis and producing an orthonormal basis with the same span. So at the bottom, what the Gram-Schmidt process lets you do is you feed it a V1 through Vn that's a basis for some space V, and you Gram-Schmidt it, and what comes out the other side is an E1 through En, which is an orthonormal basis for V. Right? So there was a process for doing that, a recursive process for doing that involved orthogonal projection. My focus, it's not everybody's focus, but my focus for you guys in this class is that you know that this is a thing that can be done. If you start with a basis, you can straighten it out into a set of orthonormal vectors. So anytime you're working with a vector space that's also in your product space, you can always assume when you have a basis that you can make that basis orthonormal because of Gram-Schmidt. So if I give you a problem and it says, hey, you have an inner product space, you can always go right out the gate by assuming not just a basis, but an orthonormal basis for that vector space, which is the content of our very first theorem. So it seems like an obvious theorem, but it's worth pointing out. Every finite dimensional vector space and it is important that we're talking about finite dimensional here. Every finite dimensional vector space, not just, we should go through every finite dimensional inner product space has an orthonormal basis. And if you want a quick proof, well, an inner product space is a vector space. Inner product space is a vector space. Every vector space has a basis. Every finite dimensional vector space has a basis. Finite dimensional vector space has a basis. V1 to Vn. Apply Gram-Schmidt. To produce E1 through En with the same span. That's the proof. Not a very complicated one, but a central fact in the study of finite dimensional vector spaces. This one is so important. I'll put a little star right here. Very important. Okay, now a related theorem that is in some sense even more useful is that any orthonormal set, you just start with some vectors that happen to be orthogonal unit vectors, can be extended to an orthonormal basis. Remember, when we're working with, one of the most important things about a basis is if I have a linearly independent set, I can always extend that to a basis for a vector space. The same game works with orthonormal vectors. So I'm going to remind you that we had a theorem that said every finite dimensional, every linearly independent set in a finite dimensional vector space extends to a basis. And so the theorem here is, sorry, I shouldn't say set, I should say list, because we're in Axler land. Every linearly independent list in a finite dimensional vector space extends to a basis. The same theorem holds for orthonormal list. Every orthonormal list in a finite dimensional inner product space extends to an orthonormal basis. And the same sort of logical game applies for this proof, which is, well, an orthonormal list is linearly independent. A linearly independent list can be extended to a basis, but that basis could be made orthonormal by applying the Gram-Schmidt process. That's basically how it goes. So the proof of this one, I'm gonna say it's left to the reader. But it basically uses extension of basis and Gram-Schmidt are the two main ingredients. And you guys should try this one. This is actually not a terribly difficult argument. Don't cheat and look at Axler. You should try this one yourself. It's useful. Okay, so the last thing I have in my notes that I wrote on 6B here before we go on is the statement, inner product spaces are awesome. So I will assert that again here. That's not inner product. Inner product spaces are awesome. Now, why are they awesome? They're awesome because you have this idea of orthogonality. You have a notion of unit one vectors. You have very easy to compute coordinates. So like linear combinations are very easy to compute. You have the existence of the Gram-Schmidt process. So you can always assume that you're working with a very nice basis. So yeah, inner product spaces have all this wonderful structure that you can use to do all kinds of things. Oh, and then I guess the big thing is we also get a notion of projection. It all sort of like builds up from the idea that we can take the idea of vector projection and do it in this sort of abstract setting. And so what we're going to do in the next section is we're going to look at how we might possibly define what it means to project onto a subspace of vectors instead. So everything that we've done up to now has been projection onto vectors. So projection onto vectors is sort of the content of 6b. Projection onto spaces is the content of 6c. Okay, so before we leave 6b behind, are there any questions that I can answer? Like, or I could ask you a question like, what's your favorite inner product space? I'll tell you what my favorite inner product space is. You guys can go look it up. It's called L2. L2 of, say, an interval from A to B. This is a wonderful inner product space. This is equal to the set of all functions f that take, say, AB into C. So complex valued functions on the interval. So that the integral of the absolute value of f squared is finite. Beautiful. This is the basis of Fourier series. All kinds of, this is the rest of your life if you become an analyst. I strongly encourage you. Do you need to know information about linear functionals? I deliberately skipped that part of the chapter, and the answer is no. You don't need to know about linear functionals. Linear functions are awesome. Linear functionals are an amazing tool, but that's a place where Axler drifts into something called functional analysis, and I think that kind of needs its own treatment as a big thing and not sort of just in passing going through. So you do not need to know the bottom part of 6b where he talks about linear functionals. Anything in that section that I did not talk about, you are not responsible for. And if I accidentally asked you a question, a homework question about that, let me know so I can go back and delete it from the set because I did not do that on purpose. I want the focus entirely to be on orthogonality and orthogonal projections and not anything about to do with functions acting on these spaces. Which hurts my soul because I give talks about linear functionals. But thanks for asking. Yeah, so don't, in fact, I'll tell you the specific pages that I don't really care if you look at here. I mean, you should look at them, but you're not responsible. So anything that comes after, so 6.37, so anything after, anything including and after 6.37 is not required. So I'm not talking about upper triangular matrices. I'm not talking about Schur's theorem. I'm not talking about linear functionals. These are wonderful theorems, but they're not part of the how I want to sort of, I want the content of the course to be nice and tight at the end here. So I'm really focusing on orthogonality and orthogonal projections. I should say this is restricted to in 6b because we're going to go on to talk about some stuff in 6c. And Chandradeep is correct. At the end of real analysis sequence. So if you take 414, you'll get to see the stuff that in much better version of it than you're going to be able to see in here. Okay, so 6c. So 6c is about, the title of this is called orthogonal complements. But what I want you to think about this is, it's a way of breaking a space up into a direct sum very naturally. The big idea of this chapter is, given an inner product, given sort of an inner product space V, in a subspace U, maybe I'll say W so it's easy to distinguish, sitting inside of V, to quickly produce V is equal to W plus some other space that's going to be called W perp. And this is a direct sum. So the idea is, the point of this chapter is that if you give me a subspace of a vector space, that I can figure out a way, not even just a subspace, but just a set, I can figure out a way to cut the vector space up into two perpendicular pieces with that. Okay. It's an incredibly useful thing to do when you're trying to work with projections. In fact, if you think about all the work it took to show things were direct sums in the past, this is almost going to feel like cheating. You just instantaneously get these direct sum decompositions of vector spaces this way. So this is kind of what we're going to be talking about for today and tomorrow. All right, so let's start with a definition. So if U is a subset now, not even a subspace, just a subset. So U some set of points. U is a subset of V. Then the orthogonal complement of U, which is denoted U with a little perp symbol up here, is the set of all vectors orthogonal to everything in U. And so what I'll do is I'll use set builder notation to build this up. So that is to say, U perp is equal to the set of every vector in V, so that the inner product of V with U is equal to 0 for all U in U. So one way of thinking about a quick picture of this, if you want to like something to carry around in your head, is if I was in R3 and I drew a plane, well, plane is a space, and that was U, you might say to yourself, ah, okay, what is the set of everything that's perpendicular to that plane in R3? Well, it turns out that that's a subspace consisting of every vector that is normal to this plane. So every vector that points in this direction is perpendicular to U. And so this is the subspace called U perp. So U perp is every vector that's perpendicular to everything that's in U. You can ask this question in reverse. If you got a line and you said, what is the set of all things that are perpendicular to a line? Well, this vector is perpendicular, and so is this one, and so is this one, and so is this one. And so you get this entire like plane of vectors that are perpendicular to everything in a line. And so the answer is, what is perpendicular to a line is a plane. So if this is U, then this is U perp. And these are two basic models that you should think of here, right? So like when mathematicians think about these things and carry them around, it's in R3, everything perpendicular to a line is a plane, and everything perpendicular to a plane is a line. Now you might ask, why just one line? Remember, if we're dealing with subspaces, 0 has to be included. So these are the lines have to go through the origin. Okay, so here's some properties of orthogonal complements. So A, if U is a subset, in fact, here Axler is going to cop out and say is a subset instead of trying to use a symbol, is a subset of V, then U perp is actually a subspace. So even if you just start with a set instead of a whole subspace, when you take the orthogonal complement, you get a subspace of vectors. B, the orthogonal complement of 0 is the set of everything orthogonal to 0, which is the set of vectors that are inner product with 0 equals 0, which is literally everything. So everything is perpendicular to 0. Or sorry, I shouldn't say that. The orthogonal complement of the 0 vector is the whole space. And likewise, The set of everything that's perpendicular to every vector in V is just the 0 vector. B. If U is a subset of V, then U intersect U perp is the 0 vector. So the set of things in U that are also perpendicular to everything in U should not be hard to believe. It's just the 0 vector. Finally,
Is that the contain symbol or an equal symbol?
no. I have no idea why Axer used the contain symbol. It should just be it's equal to the 0 vector.
Thank you.
Should have been equal. If U and W are subsets of V, and U is contained in, now I'm using the subset symbol here, and U is contained in W, then the perp of U is bigger than the perp of W. So once I take the orthogonal complement, I get larger. And the logic there is that if I start with a smaller number of points, more things will be perpendicular to them. And you can actually see that, so property E is actually the easiest exhibition here is the exhibition that we saw before, which is the orthogonal complement of a smaller set. So this set U was dimension 1. Its orthogonal complement is dimension 2. The orthogonal complement of a dimension 2 set in R3 is dimension 1. So the bigger the original space, the bigger the original set or subspace is, the smaller the orthogonal complement has to be. And that's the relationship that property E is supposed to encode. All right. So of these arguments, I think the most interesting one is the argument that this is a subspace. So let's just check it real quick. So let's check that U perp is a subspace. Now I know it's been a long time, but how do we check something as a subspace? You're going to be asked to show something for 100%. You're going to be asked to show something as a subspace on the final. There should be something permanently in there. 3 conditions.
Zero vector closed under addition and then closed under scalar multiplication.
Perfect. Okay. So let's let U be a subset of V. And let's pick. Well, I guess the first thing is we're going to show that 0 is in U perp, right? So A. 0 is in U perp because 0 inner product U is equal to 0 for all U and U, which is exactly the condition to belong to the orthogonal complement. Since U inner product 0 is equal to 0 for every U and U, that implies that 0 is in the orthogonal complement of U, just by definition. If you recall, that's the definition of the orthogonal complement. Go back up here and we'll look at it real quick. Right here. So 0 must be in there. Okay. Now let's show that it's close under addition. So let's let U, so the V and a W that are contained inside. So let's let V and W be elements of U perp, and we want to show that V plus W is in U perp. To do so, let's choose an arbitrary U in U. If I can show that U inner product V plus W is equal to 0 for an arbitrary choice of U, then that will show that V plus W is also in U perp. So we're going to compute this. And what does that equal to? Well, I can use the inner product property to pull this apart into V inner product of U plus W inner product of U. But because V and W are in the perp of U, each of these must be equal to 0. Since they're equal to 0 for every choice of vector U, which means this is equal to 0, and this holds for all U in U. That was an arbitrary choice, which implies that V plus W is in the perp of U. It's closed under addition. Likewise, if we let lambda be an F, and we need to show that the lambda be an F, and let's let V be an element of U perp. And what we want to show is that lambda V comma U is equal to 0 for all U in U. So we just do it. Lambda V comma U is equal to lambda V comma U. Well, but V is in the orthogonal complement of U, which means this inner product is always 0. So this is equal to 0. So what we've shown is lambda V comma U is equal to 0 for all U in U, which implies that lambda V is an element of U perp, which implies it's close under scalar multiplication. And so since 0 is in there, and we're close under addition, and we're close under scalar multiplication, we claim U perp is a subspace. Now, having established that U perp is a subspace, so U perp is a subspace, and we already know that U intersected with U perp is the 0 vector. The next thing we might think is maybe I can use this idea to pull V, a vector space, apart into U and its orthogonal complement. Because when I see this, I start thinking about direct sums. That U plus the perp of U is going to be a direct sum. And in fact, that is the content of the next theorem, which we don't have time to prove, but I would like to state, and then we'll talk about how the proof of it works next time. Actually, I'm going to have you guys read this proof, and then we'll talk about it in class tomorrow, which will be back in person. So let's let U be now not just a subset, but an actual subspace. I have to start with a subspace for this theorem to hold. So let U be a finite dimensional subspace of an inner product space V. Then V can be written as U direct sum U perp. And I want you to just look at that theorem for a second and appreciate how amazing that is. Like, we spent a long time. I mean, you guys on multiple exams have had to prove things are direct sums. Lots of homework questions. It's annoying to show that things are direct sums. Like, hey, I've got this subspace, figure out like what it's, you know, this direct sum piece is, where you have to run through a basis argument or whatever. Here we just get it for free. If you're an inner product space, you automatically get a direct sum decomposition of the vector space that you're working through, which is really nice because it means that every vector can be written uniquely as a piece in U, and a piece in its orthogonal complement. This is a super nice theorem. I'm going to even write that. Super. After all, you don't come to your upper division math classes to get like non-dorky statements about mathematics. So this is a super nice theorem because what it indicates is that inner product spaces are very, very highly structured. Inner product spaces are very easy to work in. And where we're going to go with this is, since I can take a vector space and chop it up into orthogonal pieces, that's going to give me a notion of projecting down onto one part of a vector space. And that's kind of the ultimate goal of all this is, I think we talked about, I wanted to make this picture make sense. Where I have a vector space, a vector V that's not inside of a subspace, and I really want to know where this vector is. And the way that I'm going to do that is I'm going to pull my vector space apart into, well, the original space that I want to work with, and then another space that's perpendicular to it. And then I'm going to project onto, like, I'm going to break V apart into the piece that lives down here and the piece that lives over here in the orthogonal complement. And that's sort of what we're going to be doing here when we start talking about this idea of minimizing distances or minimization problems. So exercise left to reader again, but this one I actually want you to read. So this in the book is theorem, let's see, where is that one? That's 6.47. So theorem 6.47. I would encourage you to read this proof. It's not a hard proof, but as Axler does, as he gets deeper into the book, as he starts leaving more steps out and trusting you guys more. So if you have questions about the individual lines, make sure you come with those questions. The hard part about this is not showing that it's a direct, it's not showing that the intersection is trivial. It's actually showing that the space breaks into the set sum actually covers the entire vector space. And that's it. Any questions about anything? I got the sneeze there. All right, well, thanks for coming, guys. This one is recorded. I apologize for not recording yesterday. I did not mean to get confused. I will put this on YouTube as soon as I get a chance to do so. And I'm looking forward to seeing you guys again in person. So, and like I said,